Okay, so yesterday we did our lab on properties of compounds. One of the tests in that lab was the solubility test. Okay, we didn't really talk much about solubility, so it was, just basically a test that we were running in order to prepare for two other tests that needed the compound in solution. But what we're going to talk about today is what is solubility. Okay, what does it mean? Some terminology, so vocabulary related to it. Okay, and also how to determine whether something is soluble or not, other than obviously putting it in water and seeing if it will dissolve. Okay, so did we notice yesterday in the lab that some things dissolved well and some things didn't? Okay, in general, which things dissolved well?
Smaller particles.
Okay, if we had something that had smaller particles, okay, what else? Did all the ones that were brightly colored dissolve pretty well? Right, the green one, the red one, and the blue one? Okay, they all dissolved pretty well. Did anything that was a crystalline solid dissolve pretty well? And hopefully, because all of the crystalline solids should have been pretty soluble, even the really big, like flying saucer shaped ones. All right. I know that one group, theirs got so hot that it actually melted the bottom of the plastic, which was kind of cool. I've never seen that before. Okay, but they were all very soluble. Okay, and so in general, we know that ionic compounds are quite soluble. There are a few exceptions. There are some ionic compounds that have a very low solubility. Okay, but we obviously know that molecular compounds can be soluble, but in general, they're not as soluble as the ionic ones. Okay, so like I said, we're going to learn terminology related to solubility today. We're going to look at what's meant by the term polar molecule, because we're also going to talk about why water is basically the exception to every rule we have in chemistry. Okay, why it behaves the way it does, right? And we're going to understand that because water is a polar molecule, it has lots of important properties, and life depends on a lot of those simple physical properties. Okay. Okay, so solubility, generally speaking, the definition of it is the degree to which something will dissolve in something else. Okay, generally we refer to that something else as water. Okay, most of the time something's solubility is measured as if it's in water. Right? Is it possible for things to dissolve in something other than water? Yeah. Okay, if you've ever painted with like oil-based paint or stain or something like that, okay, it's not water-based like latex, it doesn't come off with soap and water. Okay, what do you have to use instead? You guys need to do more chores. Never painted with oil-based paint. Okay, if you use oil-based paint or something like that, or you get something that's really greasy on you, it doesn't come off with soap and water very well. But if you use something else like paint thinner or gasoline, okay, it'll come off right away. Okay, so it's some things are soluble in water, some things aren't, and some things are soluble in other materials. Okay, anything that can dissolve something else, okay, is what we call a solvent. Right, so typically we call things that are going to be used for cleaners solvents because they help to dissolve other things. Right, so solubility is the degree to which something will dissolve in something else. A substance is said to be insoluble. Okay, if it will not dissolve in another substance. All right, so insoluble means, okay, so insoluble means will not dissolve. Okay, if a substance remains insoluble and in a solid form, we call it a precipitate. Okay, so in this picture here on the right, okay, we can see that there's this cloudy stuff here, okay, and it will eventually fall to the bottom of the test tube. Okay, we call it a precipitate because it essentially falls out of the solution and collects on the bottom like precipitation falls out of the sky. Okay, so a precipitate just comes out of the solution and then shows up somewhere else. All right, and when we do our reactions lab after the break, okay, you'll have a couple of reactions that will actually produce precipitates. There'll be two clear solutions, you'll mix them together, and you're going to get a solid powder forming, okay, when you mix the two together. All right, so a solution, so terminology here, okay? A solution is any mixture containing a solute, that's the thing being dissolved, in a solvent, that's the thing doing the dissolving, okay? So a solution is often known as a homogeneous or homogeneous mixture. Okay, so we're going to use this term a lot, okay? Homogeneous mixture or homogeneous mixture, okay? If something is homogenized, it means it has how many visible parts? One, okay? You guys may not know this because you've probably never milked a cow before, but if you like milk a cow and leave that milk, it separates, okay? The cream rises to the top, okay? Obviously that doesn't happen with milk you buy in the store, okay? And that's because all milk you buy in the store is homogenized. It's a chemical process, okay, that results in the milk not separating, okay? Same with peanut butter, right? If you get normal, like non-organic peanut butter, okay, it's homogenized. They've made it so that the oil will not separate from the rest of the chunks of peanut. Okay, if you buy organic peanut butter, it's not homogenized. You have to stir it every time you open it because the peanut oil comes to the top and all the other stuff settles to the bottom, and you have to stir it before you can apply it. Okay, so homogenized, okay, or homogeneous means one visible part. Okay, that is something is completely dissolved in something else. Okay, that sort of makes sense. Okay, and that's what obviously the prefix homo means one. Okay, everybody with me on that? All right. Now, if I mix two things together and they're not soluble, it's possible for me to suspend one in the other. Okay, but can I separate them? Okay, that's a heterogeneous mixture. Okay, hetero means many, right, or multiple. So this is one visible part. This is many visible parts. Okay, a heterogeneous mixture is often also called a mechanical mixture. Right? So if I pour oil in water and I stir it, okay, the oil will be mixed in with the water. Will it be dissolved in the water? No, because as soon as I stop stirring, the oil will go to the top again. Okay, that's a mechanical mixture. I can force them together, but I can't dissolve one in the other. Right? The same would be true with the example they have there. If I put iron filings in sand. Okay? If I put iron filings in sand and mixed it up, the iron is mixed in with the sand. Okay? Is it dissolved in the sand? It's not. Okay? Could I separate them pretty easily? Okay? How would I separate iron filings from sand?
Magnet.
With a magnet, yeah. Just stick a bar magnet in there, start stirring it around. Pretty soon all the filings will be attached to the magnet and they'll be separated from the sand. Okay? With oil and water, all I have to do is leave it for a little while, let the oil rise to the top, and I can pull it off. Okay, and separate it from the water. If I dissolve salt in water, can I separate it after?
Yes, with desert tun, or
If I distill it?
yeah.
Yeah. Okay, I can separate it, but it's going to involve a lot greater use of physical properties to do it. Okay, so once I've dissolved something in something else, okay, basically the only way to separate them would be to change one of their states, boil off the water and leave the salt behind. Okay? But with mechanical mixtures, they're much easier to separate. Okay, so one on the left here, this is our homogeneous mixture or a true solution. Okay, this is a heterogeneous mixture on the right, or a mechanical mixture because it has two or more visible parts. Okay, everybody all right with that idea? Okay, so we got to be familiar with those terms. Okay, and then more terminology here. The solute is the substance being dissolved. Okay, so if I add sugar to coffee, sugar is the solute, coffee is the solvent. Okay, and then the solvent is any substance that dissolves another substance. Okay, water is often referred to as the universal solvent. Okay, it dissolves most things. Okay, and like we said, oh shoot, I lost my train of thought. like we said, cleaners, okay, are often referred to as solvents because they help to increase the solubility of whatever it is you're trying to clean off. Okay? If you tried to clean like a really dirty shower that had a lot of like hard water scales and soap scum on it with just water, would it be a lot of work? And you probably wouldn't be successful. Okay? You're just not going to get soap scum to dissolve in water to the extent you need it to dissolve, okay, in order to get rid of it. Right? So instead we add things to the water, you know, CLR or Mr. Clean or whatever solvent you use, okay? And that helps to dissolve that stuff. It makes it more soluble in the water and it's easier to take off. Okay, questions on that terminology? Okay, could Tuesday's quiz possibly contain terminology related to this? All right, now for a precipitate is a solid that's produced in a reaction and will not dissolve in solution. All right, so I was telling you before, okay, you're going to have in our reactions lab 2 reactions where you're going to mix 2 clear solutions. And when you mix them together, you're going to produce solids, okay? Precipitates that are going to be powders that you'll be able to visibly see fall out of the solution after the reaction. So what you've done is you've taken 2 materials that are soluble in water, caused a reaction that produced at least 1 material that's not soluble in water. Okay, now that happens through a process like this. Okay, so if I take this stuff here, okay, lead 2 nitrate, and I react it with potassium iodide, okay, a reaction occurs where, just like Dalton said, atoms are going to be rearranged. Okay, the atoms are going to be rearranged like this. Lead will end up with iodine, and potassium will end up with nitrate. Okay? This stuff is soluble. So is this. Those are your 2 clear solutions. After the reaction, you produce this stuff, which is soluble in water, and this, which is not. In fact, it's a bright yellow precipitate, a bright yellow powder. Right? So what we've done is take 2 things that have physical properties of this is soluble, and we've produced 2 new materials, one of which has solubility or is soluble, and one whose physical property is that it is not soluble in water, or at least not very. Okay? And so as a result, it precipitates out of the solution. Okay, so I'm going to show you kind of what that looks like. I've just got like a quick YouTube video of it here that I'll show you. I'm mixing some stuff together and you can actually see the precipitate form. It's not a life-changing video by any stretch of the imagination. Okay, and it's got this really strange background music that's like not fitting to the video. You'll see what I mean when you watch it. Okay, so now you kind of see what a precipitate forming is going to look like. That's less obvious than the ones we're going to have in our lab. Okay, the ones that we do in our lab, it's like basically clogs the tube. Okay, it forms such a thick precipitate. Okay, so like I said, the definition for solubility is the degree to which a substance will dissolve in another substance. That is how much solute can go into solution before the solvent becomes saturated. Okay, if something is saturated, what does that mean?
It's reached its max absorbing capacity.
Right, it can't absorb anymore. It can't take anymore. Okay, now we usually use the term saturated to refer to for like soaking wet. Okay, and it still applies. If your clothes, let's say, are saturated, you're dripping, okay? Because your clothes can't hold any more water. They're saturated, okay? Well, the same is true for a solution. I was telling you how I make Kool-Aid, okay, the other day, right? I use hot water, I add the Kool-Aid, and then I add the sugar until, okay, the sugar starts to form on the bottom. I saturate the solution. That water can't hold any more sugar. Okay? And when I cool it off, even more falls to the bottom because solubility is affected by what? By temperature. Yeah, the hotter something is, the higher the solubility will be. And that's simply because the particles inside are moving faster. As the particles move faster, solubility increases. As the movement of the particles decreases, then the solubility decreases. Now, some things should be soluble, and some things shouldn't. Okay? How many people have ever eaten a Twinkie? Yeah, you can probably admit it. I mean, Twinkies are yummy. Twinkies today are not like their original creation. Okay? The original Twinkie was cake with filling. Okay? What's cake usually made of? Flour, milk, eggs, butter. Okay? Natural ingredients. Okay? And the filling was butter and sugar and cream, basically. Okay? All natural ingredients. Okay? Now, butter, cream, eggs, are those soluble in water? If you crack an egg into a glass of water, it's float on the top, doesn't dissolve, right? The egg doesn't dissolve in the water. Okay? Same with cream. Cream doesn't dissolve in water. Okay? It'll mix with it, but it won't dissolve in it. Okay? Butter doesn't dissolve in water. Okay? So by that definition, a Twinkie shouldn't dissolve in water. And the original Twinkie didn't. It would act like a sponge. We put a Twinkie in water. Okay? It'd suck up all the water, and then it would be this big, giant Twinkie. Okay? Filling a glass would be all soggy like a sponge. Okay? Well, the problem with the original Twinkie was it was made of real things. And it didn't last very long on the shelf because it would mold and rot, things that natural stuff does. Okay? So if you're Hostess, the company that makes Twinkies, that's bad because you lose a lot of your product before it's sold and you don't make as much money because some of it gets wasted. So they started looking at ways to replace some of the natural ingredients with, let's say, more artificial replacements. Okay? How many people have ever had powdered eggs? Okay? I mean, they're like real eggs, but they're not exactly real eggs. Okay? How many people have had powdered milk? Okay? It's like milk, but not really. Okay? So what they've done is they've essentially taken these natural ingredients, they've replaced them with things that are artificial. These things that are artificial are similar enough that the Twinkie still tastes pretty much like it originally did. Okay? But because there's not as much organic stuff in it, it lasts longer. Okay? Plus, they add a preservative to it. Okay? The preservative they add to it is the same stuff that's in mortician's fluid. What's mortician's fluid used for? Yeah, it's used if someone dies and their funeral isn't for a few days. It keeps them from getting smelly. It preserves them. Okay? It's a preservative. That same stuff is used in small amounts in a Twinkie. It's not going to kill you if you don't eat lots of Twinkies. Okay? Everything in moderation. If you eat 5 Twinkies a day, Twinkies are not good for you. Okay? If you eat that many a day because they've got that preservative in them. And the stuff that they replaced eggs with doesn't have the color of eggs. I mean, the reason a Twinkie is yellow is because it used to be made with eggs and eggs are yellow and they made the batter look yellow. Okay? The stuff they replaced the eggs with is the color of drywall paste. It's gray. Nobody wants to buy a gray Twinkie. So they add yellow dye number 5 to the mixture to get the color of the Twinkie back. Yellow dye number 5 is banned in most European countries as a food additive because it's a known carcinogen. Okay? That means it causes cancer. And it's really bad. Right? So if you're eating a lot of Twinkies, you're like slowly poisoning yourself. Okay? 1 Twinkie, not so bad. Okay? 1 Twinkie here or there, but 5 Twinkies a day, you have a problem. Okay? So the modern Twinkie, if you put it in water, will actually dissolve. Okay? It's made of materials that are soluble in water. Okay? And it will actually dissolve in water, unlike the original Twinkie, which would have just swelled up like a sponge. Okay? So some things should be soluble, some things shouldn't. Okay? This is probably one of those things that shouldn't be soluble, but it is, because it's the natural stuff that was molecular has been replaced with things that are not. All right. I just wanted to gross you out. All right. So on your periodic table, on the back of it, if you can take this out, is something called our solubility chart. Okay? I'm going to show you how to use that. It's going to be something you're going to need to be able to do. Okay? From time to time, we have to be able to figure out whether a material is soluble in water or not. Okay? Especially if it's a product of a chemical reaction. So if we're moving towards chemical reactions next week, or the week after next, okay? And so we need to be able to determine whether something is soluble or not, because we need to be able to predict whether a reaction, is going to produce a precipitate or not. And that's what this chart is for, okay? So the chart is set up so that the negatively charged ion, or non-metal, is the top row of the chart. Okay, so this is only for ionic compounds, obviously, because molecular compounds are not always soluble. Okay, so we've got all the negatively charged or non-metal ions up top. Okay, the next two rows are the positively charged ions that they might be paired with. Okay, if the negatively charged ion is paired with something in the first row, it will be soluble. That means it will dissolve in water. Okay, or be very soluble. If the negatively charged ion in the top row is paired with something in the third row, okay, the bottom row, that stuff will be insoluble. In other words, it will form a precipitate if that compound forms. Right? So if we're looking at these two examples right here, okay, iron 2 sulfide and sodium hydroxide. Here's how I use the chart. I want to determine whether iron 2 sulfide is soluble in water or not. Okay? Which one of these things is the non-metal? Sulfur. Okay, so I go along my top row until I find sulfur. It's right here. Okay? Then I look to see where iron, the thing it's attached to, appears. If it appears in the first row, that compound is soluble. Does iron appear in the first row? It doesn't. Okay? So if it's not here, then iron must be down here with most. Okay? Which means that iron 2 sulfide is basically not soluble. Okay? If I put it in water, it would not dissolve. If I formed it in a reaction, it would become a precipitate. Okay? It would become a solid and fall out of the solution. Okay? For sodium hydroxide, okay, hydroxide is my negatively charged ion, so I go to the top row and I find hydroxide, okay, and in this compound it's paired with sodium. Sodium is right here. Okay? So is that compound soluble or not soluble? It's soluble because it's paired with something in that second row. Okay? Everybody follow how that chart works? It's not rocket science. Okay, so here's what I want you to do. Okay, using your solubility chart, I want you to write soluble just with an S or N for not soluble. So S or N next to these things based on whether they are soluble or not. Okay, give you a couple minutes on that and then we'll walk through it. Okay, so our first one, we've got lithium fluoride. Okay, so I go up to my periodic table, I find fluorine. Okay, it's right here. And so it says it's soluble with most things, which kind of isn't all that helpful. Okay, I have to then look down here and see, is lithium in the second row, or the third row, sorry, and it is. So is this substance soluble or not? It's not soluble. Okay, for number 2, sodium sulfate. Okay, so I find sulfate. Okay, sulfate's right here. It says it's soluble with most things. Okay, I look down in this row here. I don't see sodium in the not soluble row. Okay, so this stuff is soluble. For ammonium nitrate. Okay, so nitrate's right here. Okay, and it says it's soluble with most things, but not these really complex looking monsters that we would never even deal with. Okay, so is that stuff soluble then? It is. Okay, and then we've got silver chloride. All right, so we look for chlorine. Chlorine's right here. It says it's soluble with most things, but not with copper or silver. Okay, so this stuff is then not soluble. And then we've got lead 2 iodide, okay, which I actually already showed you is not soluble because it was in that reaction I showed you. Okay, but iodine's right here, soluble with most things, but not with lead 2 plus. Would it be soluble with lead 4 plus? Yes. Okay. If it's not listed there in the second row, it would be soluble with that. All right. For number 6, H2S. All right. So we look up here for S. Okay. Here's S, soluble with hydrogen. Okay. So that one is soluble. Number 7, we've got potassium phosphate. Okay. Phosphate is right here. Okay. It says it's soluble with potassium. So that stuff is soluble.
Just,
Our
yeah.
chars don't have sulfur.
It doesn't have the sulfur on it?
No, it just goes
It
from the
doesn't have a lot of
IO3 to
things.
OH. So.
Oh, yours says group 1. Okay, sorry, right. Okay, group 1. This is group 1 on your periodic table. Okay, first column, group 1. Second column, group 2. Okay, so if you see group numbers in there, that's what it means. Again, I think it only ever says group 1 and group 2, right? Okay, so group 1, first column, group 2, second column. Okay, and then our last one, okay, we've got mercury chloride, mercury 2 chloride. Okay, so we find chlorines right here, soluble with most things, but not with mercury 2+. Right, so that stuff would be insoluble. All right, pretty clear on how to use that? Okay, that's going to be one of the analysis questions on your reactions lab. Okay, you're going to have 2 reactions that produce precipitates, and I'm going to want you to figure out what compounds those precipitates are using your solubility chart. Okay, so that's where we're headed with that. Okay, now we got to talk about water. Okay, water and its weird behaviors and structure. Right, water is a molecular compound. Okay, we know that because it doesn't conduct electricity. Okay. When hydrogen and oxygen bond together to form water, okay, that's a covalent bond. It's a molecular compound where the electrons are shared. Okay. For most molecular compounds, that sharing is pretty equal. Okay. Each one of the atoms gets to have the electron about the same amount of the time. That's not true for polar molecules. And water is a polar molecule. Okay. If something is polar, that means it's got one extreme and then another extreme. Okay? And for water, that means that one end of the molecule is positively charged and the other is negatively charged. And the reason for that is that the sharing of the electrons isn't equal. Okay? Hydrogen shares its electron with oxygen, but oxygen doesn't share it back very well. Okay? The electrons spend way more time around oxygen than they do around the hydrogen atom. Okay, so if this is our shared electron, okay, this one right here, okay, it doesn't really do this where it kind of orbits and stays kind of equidistant from there. Its orbit is more like this. Okay, it spends way more time around oxygen than it does around hydrogen. Okay, and effectively, it doesn't even go around hydrogen like that. It actually does this. Okay? It really becomes mostly oxygens. Every once in a while it gets near the hydrogen atom, but not much. Okay? Which means for both of these hydrogen atoms, that electron that they are sharing, okay, doesn't end up on the top of them very often, like never. So what you have is a water molecule that's got 2 positive points at the top and 2 negative points at the bottom. Okay, that's why we get the term polar molecule. The top of the molecule is positive, the bottom of the molecule is negative. Right? Because of that, water can be attracted to other polar molecules, including itself. Okay? If another water molecule comes along and it's oriented like this, okay, its negative end will be attracted to the positive end of this water molecule. Okay? And they'll come together. How do we see that? What does that look like when it happens? It's a behavior of water. You ever notice how you can fill a glass more than full with water? Just slightly more. What's that stuff on the top called? Surface tension. Yeah. Okay. Surface tension is the result of what's called a hydrogen bond. Okay, and it's a bond between the negative end of one water molecule and the positive end of another. Okay, this forms a weak bond, like that. Okay, it's weak because we know like you touch that surface tension and it breaks. Okay, it reforms quickly, but it's not very strong. Okay, but that's the result of water being a polar molecule. Okay, how many people have ever accidentally frozen a water ball? Okay, what happens to the water ball? It breaks. or the bottom of it punches out, right? Okay? Because what does water do when it freezes?
It expands.
It expands. What do most things do when they turn into a solid? No, most things contract. Okay? Most materials are in their smallest form when they are a solid. Most things shrink when they turn to a solid. Water expands because it's charged. Okay? This water molecule right here can only get so close to this one before the negative ends will start to repel each other. Okay? That happens at about 4 degrees Celsius. So water takes up the least space at 4 degrees Celsius when it's a cold liquid. Okay? Below 4 degrees Celsius, the water molecules start to move away from each other because they get too close, and there's actually almost like an elastic rebounding effect, okay, that occurs as the water starts to freeze. So as it gets close to freezing, the water molecules bounce away and the water expands into a crystalline solid, okay, that takes up more space than its liquid counterpart. Now, that's kind of important for life on Earth because it means that ice will always be where compared to water? You put ice cubes in water, where do they go?
They float.
They float. Okay? The solid form of water is less dense than the liquid form. That is exceptional. Most things, if you had the solid form of it and you dropped it into its liquid form, it would sink to the bottom because it would be more dense. It would contract. Okay, and be more dense. Water's the opposite. Because of its polar nature, it pushes away and expands. Okay, which is important because imagine if it wasn't that way, lakes would freeze from the bottom up. Okay, fish would never be able to survive the winter. Okay, it would really change aquatic life cycles. Okay, because you would never have ice floating on top. Well, it would always be on the bottom, and that would mean that lakes would freeze completely solid. Okay, as opposed to they freeze a little bit on the top and the liquid water is preserved beneath. All right, so this is what we call a polar covalent bond. Okay, the electrons are not shared equally. Okay, so sharing is not equal in a polar covalent bond. So some materials are more electronegative than others. And electronegativity is actually a physical property, and it's listed on your periodic table. Okay, so if you look on your periodic table, okay, right underneath the atomic number is a number. Okay, so for oxygen, that number is 3.4. Okay, right below the 8. Okay, oxygen's electronegativity is 3.4. Hydrogen's is 2.2. Okay? Electronegativity is how hard that material holds on to electrons. So does oxygen hold on to electrons more strongly than hydrogen does? It does. Okay? Oxygen is one of the most electronegative materials there is. Okay? It's a very high electronegativity, so it holds on to electrons really hard, okay, and doesn't let other materials have them, even though they're technically sharing them. Okay, this is like buying a pizza with the friend that has no problem eating most of it, okay, and leaving you like 2 pieces out of the 8. Okay, that's how this relationship works. Okay, so there's polar bonding where the electrons are not shared, and then there's hydrogen bonds that can happen because of that. Okay, those hydrogen bonds are what lead to surface tension. Okay, and another thing called adhesion. Okay, have you ever had a really cold drink? Okay, a really cold glass of water, you notice that water starts to condense on the outside? Okay, but do the drops run down right away? They kind of stick to it, right? They can stick there until they get kind of too big and then they come down. Okay, that's because of hydrogen bonding. The water molecules hydrogen bond to the glass. Okay, and those bonds are strong enough to support the water droplet until it gets too big and then they break, and then the water droplet slides down the glass. Okay, but it's again another hydrogen bonding polar molecule type behavior. Okay, you see that when there's dew on the surface of a leaf, right? It makes that bead of water, okay, and it stays there until you disturb the leaf and then it runs off. Okay, all of that is that same hydrogen bonding thing. Okay, so the water molecule ends up being shaped at essentially a 90-degree angle because these two positively charged hydrogen atoms repel each other. Okay, they push each other away, right? And then on this end, the same thing happens. Those extra electrons repel each other, okay, and they keep the water molecule at a 90-degree angle. So one water molecule can hydrogen bond to 4 others. Okay? And this is important for plants when they're trying to transport water from their roots to their leaves. Okay? How many people have ever tried to drink out of a really, really wide straw? Okay? Is it, like, I mean, if the substance is really thick, that it's better to use a big straw. But if you're just trying to drink like a liquid with a really big straw, is it very easy? No. But with a little straw, it's very easy. Okay? And the reason for that is water can bond to itself, again, but those bonds are not very strong. If you have a very small straw, the column of water that's in it isn't very heavy. The hydrogen bonds are strong enough that it can support most of that column of water and make it easier for you to draw the water through the small straw. But the wide straw, okay, there's too much weight inside, too much unsupported water in the middle. The hydrogen bonds aren't strong enough to hold it, so it tries to fall back down. Okay? So you actually have to create more suction in order to be able to draw liquid up a wider straw. Okay? So what plants do is they have these microscopic tubes in their stem that allow them to transport water. And they use the fact that water can stick to itself as well as the inside of the tubes. Okay? And so it supports itself and defies gravity, essentially, allowing the plant to pull the water from the roots without using any energy. Okay? It uses the polar nature of water to do that. Okay, so we talked about this, why water expands, okay, hydrogen bonds, okay, hydrogen bonds are important, okay, and then this is what we just talked about here, okay. There's these two behaviors. There's cohesion and there's adhesion. Cohesion is when water bonds to itself. Adhesion is when it bonds to something else, okay. So when we're looking at the inside of a tube, inside a plant, okay, there'll be cohesion here between two water molecules. There'll be adhesion here when the water molecule bonds to the inside of the tube. Okay? Essentially what it does is it makes water look like the barrel of monkeys. You guys ever play with that when you were a kid? The monkeys with the arms and you can hook them together. Okay? It essentially makes all the water molecules linked all the way from the leaves to the roots. And if one of them moves, it pulls all the others up because they're all hydrogen bonded either together or to the inside of the tube. Okay. Have a good week off, guys.